Good afternoon. Meine Deutsch ist schlecht, so we'll take this in English. If you have questions, just feel free to interrupt. We can be very reactive for answering questions. I don't mind at all. First, to introduce us, Ampere. So who's heard of Ampere? Who's familiar with what we do? Maybe about half and half. So we're a silicon design company. And what that means is that we design and create CPUs, and we aim those CPUs for the data center, for cloud applications. And we're regarding ourselves as a startup. When you start up a silicon design company, there's a lot of work, and it generally takes 5 or 6 years to get to the place where we've got now. We're 3-4 generations of silicon in, deployed and sold on time. That really is quite a strong press, isn't it, there? As I say, we're a startup, but we have tremendous experience in the industry. We have executives, we have engineers like myself, and we have sales and marketing professionals that have been in the data center industry, in the silicon design industry for many, many years. So we're bringing a lot of experience to the designs that we bring to market. We're worldwide and have presences in Europe as well as the Far East and the Americas. And in fact, we're a Silicon Valley-based company ourselves. What we were set up to tackle and what our designs are primarily focused on are providing energy efficiency and providing performance and density in a data center environment. And that is our almost sole focus for the designs from our company and for the systems on a chip that we produce. And the reason for that is that our founder and some of the people with her thought that data center power demands, CPU and GPU, and all the networking equipment were just getting far too great, and that there are better ways to design silicon, better ways to design cores, so that you can start at the core of the data center with some power efficiency, and then have that power efficiency and lack of power demand spread out to all of the other components. And we're seeing some of the symptoms of data centers rubbing up against the societies that they're built in and causing friction. Right now, you know, data centers just use maybe 2 or 3% of worldwide generated electricity, but that's growing tremendously. We see here some simulations of what we're going to be like by 2030. Data centers at least double, triple, or quadruple, possibly 10x by 2030. It just depends on things like the world economy, things like innovation. But that's the trajectory that we're on, and it's not good enough because in the UK, in Frankfurt, outside of London, in Ireland, around Dublin, housing estates, people can't get houses because housing estates can't be built because the power's not there, because it's already been taken by data centers. And it takes decades to put good power infrastructure into new places. So we have an issue to deal with. Along with that, we have software always continually changing. And software, the changes in the way the software is developed and deployed, drive the changes and the reactivity of the hardware to more efficiently house that software. This is something else that we've been very keen on exploiting at Ampere, And as we've gone from mainframe to the very traditional 1990s client and server and through the noughties into what we call our modern cloud environment and on into hyper-converged, we see software services being decomposed into tinier and tinier amounts so that you have many multiple threads dealing with all of those smaller composable pieces of software. So you need many cores, you need a lot of density within your server, within your rack and your data center. These are what we've designed for, and the issues that the industry has, the hardware industry have, they have put on limitations that have created extra power demand for CPUs and limited the scaling that we've seen for the last few decades. So what we've seen up until now is turboing in frequency, so that one thread gets more resources than any other thread can get. But that gets workloads through a little bit more quickly for some workloads. Hyperthreading too, when you're waiting on memory to come back with an answer for something that's not already in cache, can help in some circumstances. And accelerators, you know, we see GPUs and ASICs coming in for AI processing, and more of that is being gobbled up by the CPU. But again, that's a lot of transistors that you're putting onto a design at the expense of being able to be more dense in your processing, more equitable in the instances and the virtual machines that you give out to your customers. So we take a different approach. You know, we're cognizant. We realize that frequency scaling and transistor scaling have slowed down. Frequency scaling appears to have kind of economically stopped. We design for consistent performance, having lots of threads with equal access to all of the resources that they need to complete their software workload. We want good separation between those threads. We don't want them to be interfering with each other's cache, with each other's frequency, so that we can scale linearly. One of the things that we're very keen on in Ampere is, you know, we design big silicon chips, 30, 50, now more billion transistors on a processor. And we want you to use all of those transistors all of the time. So we're very keen on you being able to use all 128 of our cores, which is what we're scaling up to at the moment, all of the time at their maximum frequency. And in this case, we'll go up to 303 gigahertz. We have a number of SKUs of chips. We go from 32 up to 128 cores. And so 32 and 64 are very power efficient for use at edge and for use in co-location facilities where you're wanting a very small power footprint. Through to main data centers, 128 cores, 3 gigahertz, all of those cores with large private caches, but crucially, the design, the architecture on those cores means that we can keep our power demands down to below 180 watts, which is quite a change for this industry when we see CPU power demands now approaching 400 watts, and they're projected to go to 600 watts in the near future. And with all of that parallelism, all of those cores, one of the things that we do get is a different kind of scaling. So for power efficiency, for data center throughput, or for rack throughput, or platform throughput, We concentrate on this performance per rack. You know, we mainly sell to the hyperscalers and the cloud service providers, and then those companies, those manufacturers who are providing cloud services to themselves. And what we're seeing in a number of our primary workloads, Nginx, acceleration like Memcached or Redis, Cassandra, and then a database backend, is that acceleration from concentrating on throughput and isolation and predictability of performance. So you see here one of the other benefits from moving to Ampere is the fact that your footprint in the data center comes down again. You can get, say, in your 12 or your 18 kilowatt rack, most of those units, most of those 42U filled up, as opposed to racks these days where you've got half of the rack filled up and the other half is a blanking plate. So what workloads are we good for? About 80% of what modern compute is. So we've gone for that largest part of the data center market, the standard compute that you would expect to be done in a value for money, in a performant way, but now with less CO2, with less power demand. Web applications, databases, the in-memory caching, the Redis, Cassandra, and the like. We are built for these applications in both containerized and virtualized workloads. And then because the scope of applications is now expanding, media encoding, transcode is important, and also the ability to infer, and infer both vision, natural language processing, and audio streams as well. So we've made deliberate architectural decisions to have acceleration for those key general compute workloads in the data center. It also helps being ARM native. And we are an ARM engineering licensee. We are ARM compatible. And it doesn't hurt that because of that compatibility, we also do Android in the cloud, native cloud gaming quite well. So we don't just throw silicon over the wall and expect our partners like Boston to pick up the pieces and be able to deal with it. We foster a community out there, and we work with partners all the way from, as you can see, operating system and firmware, both open source and closed source firmware, all the way up through the infrastructures, the OpenStacks, the Dockers, the Podmans, Singularity for more scientific containerized workloads, through to the languages that they're built in. We're committers to these open source projects, as well as higher up where we'll work with WordPress to help them get the most out of our processors when they deploy on us. And these are things, you know, that we're keen to demonstrate publicly. We do nightly builds. We publish the results of those nightly builds so that you can duplicate and you can trust what we're building so that you can build that for yourselves, for your own customer environments. And so with that approach, who's taken us up? We've had some pretty good success so far. We are in Google Cloud Platform, Azure, Oracle Cloud, and many of the Chinese hyperscalers as well. I'm proud to say, and I've worked on them myself, we've announced just this year, well, in fact, going back to last year, in Germany, Hetzner and Ionos, And then other European companies coming on board, G-Core, LeaseWeb, Gliesis up in the Nordics, who are using our processors along with zero carbon power and then shipping the heat that's generated back into their local grid. I mean, that's the way it should all be run, yeah? And then, you know, we go to market through channel partners. And Supermicro has been a long-time partner. They're building our roadmap machine at the moment. They have also got our single-core machines. But through Supermicro and Foxconn, we're able to bring you the Fenway range of servers from Boston. So really, for a little bit of a summarization, focus on that rack-level performance, that rack-level throughput, and actually filling your racks up again. Because it's, at the end of the day, performance per thread is great for some workflows, and it's okay on the desktop too. But that doesn't make for an efficient data center. And the changing of your view of where you get scale and where you get power efficiency means that focusing on that performance per rack becomes very, very, very important. So, how can you start with us? My thumb's going to sleep. On the website, but also with Boston as well. But we have a number of facilities that will help you get started. There are cloud instances out there that you can sign up for now, for free as well. Try Oracle. But learn about what we're built for. Learn about where our efficiencies are. You can plan your own migration through our solutions portal. And engineers like myself and my colleagues, we're also here to help and advise you through that set of migration steps as we've done with other customers before. You can see some of our performance in the workload briefs and how to duplicate what we do, how to duplicate what we are able to show being built every night to engender that trust in the architecture. And then go deploy. And there's a number of places to try. As I say, we're available in multiple clouds. We're available from OEMs and ODMs, and also systems integrators in region with partners like Boston who can focus on the RFPs and the use cases that you guys or your customers have got to go win. So I'm available for one night only. I'm over in the conference room 1. I can take you through the dual socket system that we have there, the Boston Fenway business line dual socket server, and I'm happy to talk more. I've got 47 seconds. One question. I must have explained it okay. Thank you.